I guess.
Did you get a haircut?
No, not recently. Oh. Nope, same old hair. I usually wait till it grows unbearably long before I get a haircut.
Do you still have these headphones? Like years ago?
Yeah, I still have them. They're my wife's headphones, they're not mine. I still have them. They mostly sit in a box though. I think she bought it for like a cosplay or something. She never actually uses it. I'll ask her.
These headphones can stand. So they can just talk shit. Touch them. Just, follow them, I'll take a picture. So just unroll. Just come up good. Would you like to just come? So.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Pretty good. Good, good. Right. So is better than not so good. So that's good. Right. So it's Tuesday of week 7, and so what I thought today we do something a little bit more lighthearted today because I know we have the midterm on Thursday, and so we're going to talk about balance today. And so we're going to talk about how your body keeps balance and how you can compute some quantities related to that. Okay. So of course, the balance stuff is not going to be on the midterm. And so our midterm is this Thursday. So remember, it is going to be an in-class midterm. And so you have to show up here to take it. And so there's no plans to offer it online. So please don't be in the Zoom room on Thursday because I won't be there. I'll be giving the exam here. So if you're on the Zoom room, then you better book it to campus because that's where the exam is going to be. And so just a reminder for the midterm, you can have your writing utensil, you can bring a calculator, and you can bring one 8.5 by 11 sheet of notes. And so you can write on both sides, you can write it, you can type it, whatever you want. And so that's what you're going to be allowed with on the exam. Okay. You probably got the email today, but I recorded the review video this morning and then I posted it on YouTube. And so that's available for you. So basically I looked at the poll this morning and basically everyone wanted me to cover more examples with static biomechanical analysis. And so what I did for the review video was I did one of the homework problems, but I did it in a lot of detail. So a problem that I think probably if you kind of knew what you're doing would take maybe like 5-10 minutes. I talked about that same problem for 50 minutes. So just going over through just every bit of my thought process and every little detail. And so whichever part you're struggling with, either with moment arms or with the angles and everything, what I hope is that example kind of gives you a lot of context and a lot of help with those aspects. Okay. So definitely check that out if you haven't had the chance yet. If you haven't checked it out yet, I would definitely check out the study guide for the midterm as well. And so remember, This midterm is a little bit different than a lot of the midterms I've given before in that most of it's going to be on conceptual questions. Remember, 60% of the points will be on conceptual parts. And so, having a good understanding of the conceptual learning objectives will help you a lot on the exam. Okay. All right, and so that's all my announcements. And so are there any questions I can answer before we get started today? Yeah.
How many questions are there?
There are 6 short answer questions and 2 problem solving questions. Mhm. Okay, all right. And so, actually, before we do balance, I did promise you that I would finish up the lecture slides from last time. So let me go ahead and do that. And so last Thursday, we were talking about injuries to the neck and spine. So let me go ahead and share my screen here. Okay. And so, just like we did with the upper extremity notes and the lower extremity notes, I wanted to finish up talking about spinal biomechanics by talking about some common injuries. Okay, so last Thursday, we talked a bit about lower back pain. We talked about how it's, one of the most common, injuries that people face here, here in the US and around the world. And a lot of it's due to, how people conduct their work and, a lot of other factors. Okay. We talked briefly about fractures. And so remember, fractures of the spine are not too common unless you have a very kind of traumatic injury, but it can happen. And because of how the spine operates, it doesn't really have a lot of blood vessels that go to it. It takes a while for spinal fractures to heal. So that's something to be aware of. But the last 2 injuries that I want to talk about most today are, ones that can happen a lot. And so the first is a hernia. And so, we talked, I know we talked about this a bit last week, but I kind of wanted to show you kind of some images of it and kind of talk about it a bit more. Okay. So disc herniations, at least at the time of when I wrote this, these notes, account for about 1 to 5% of back pain, okay? Which doesn't sound like a lot, but people that do have hernias exhibit very, very debilitating pain. And so, my uncle has had hernias before, and he basically just can't walk at all. Right? And so what a hernia is basically is that, remember what we talked about last week, we had these, intervertebral discs. And so we have these kind of cushions that occur in between the vertebrate bones in your body. And the purpose of those discs is to kind of soften up any kind of the compressive impacts that you might experience, throughout the day or throughout your work activities. Okay. What can happen is that if you put a little bit too much compressive stress on the vertebrae, then it can kind of literally push out and squeeze out this disc from its socket. And then if you do that and it kind of starts to impinge on your spinal cord, it can cause a lot of pain. Okay. And so I want to, I think, I want to clear up one misconception here. So even though it's your disc, the one that's, being injured and the thing that's protruding out, the disc itself can't really feel any pain because there's no nerves that are actually inside your disc. It's literally just cartilage and kind of fibrous kind of pushy stuff. The part that actually causes you pain is the fact that the disc starts pushing up against your spinal cord, which is a nerve in your body, and in fact it's the biggest nerve in your body. And so you can imagine if you're putting pressure on that nerve, unnatural pressure, then that's going to cause you a lot of pain. Okay. And so disc herniations, they can be caused either by, one kind of extreme event, so any kind of traumatic injury that pushes your spine together, or what's more common is that it's caused by a lot of repeated stress. And so, we talked a lot about posture last time. If you have poor posture when you're going through your working day, or if you have poor posture when you're working out, say you're doing like a deadlift or something, then you do this kind of repeatedly, and this is what can cause a disc herniation. Okay. And so the most common place for this would be either in the cervical vertebrae or the lumbar vertebrae. I think between those, the lumbar is more common just because that's in your lower back. Okay. And what's difficult about the herniation is that it doesn't cause any kind of visual cues. And so the reason I mentioned this is that, the herniation is usually not something that occurs, suddenly. And so it's not that, you're fine, and all of a sudden it's like, and it all just kind of spurts out like that. It's actually typically kind of a slower process. And so, especially the ones that occur through repeated stress And so kind of as you go about your day and as you kind of, you have bad posture and everything, the disc kind of slowly kind of leaks out more, but you only really feel pain once it starts to push on the spinal cord. But even so, even with that, it's very hard for doctors to diagnose this, because as that disc gets more and more pushed out, if you take an X-ray of the spine, if you take an MRI of the spine, you actually don't really see all that much, because what doctors are kind of looking for is that is the space in between your vertebrae bones, are they changing at all, right? Because you would think that if you're kind of squeezing the discs together, the space in between would decrease, but you don't really see that in a lot of the X-rays, and so it can't really be detected. And so in terms of treatments, a lot of the treatments just involve just kind of good rest and just kind of helping and some good physical therapy to kind of help encourage the disc to kind of go back inside on its own. But in some very severe cases, then surgery is an option, but that's only for very, very severe cases. All right, and so the last spinal injury that we'll talk about is whiplash. And so whiplash is, I think everyone's kind of familiar with this. This is an injury in your neck, and that occurs when your head kind of goes through sudden motions, a sudden acceleration, deceleration, which can cause some injury to your cervical spine. Okay, and so what it is basically is that because you're having such intense movements of your head, it causes a lot of shearing forces, an extension at the junction of the cervical spine that it typically does not it's not used to. Okay. And so the most common place where this happens is through an automobile accident. Okay? And so I think one thing that we don't really realize that when we're driving a car, especially on the freeway, we're actually going really, really fast. And then if you get into an accident, then that's a very sudden kind of deceleration of your entire body. And so in that case, your head might be kind of lagging behind the rest of your body, and you might get whiplash from that way. Okay? And so the symptoms from whiplash include things like neck pain, muscle pain, any kind of pain and numbness, radiating from neck and shoulders. So anytime you have kind of, pain in your neck and you had a car accident recently, it's probably that. Okay. All right. Any questions on hernias or whiplash? Okay. All right. And so that's it for the spine. And so, I know it was kind of very quick, but I wanted to make sure we go over that especially because I know it is on the study guide. Okay, so let's come back here and let's start talking about balance. Okay, and so, balance, again, I consider this kind of a more fun topic. There's not really any big intense calculations. There are some calculations, but they're not that bad compared to what we've seen. And it's kind of more just for fun. So I don't plan on testing you on any of this, especially not on the midterm on Thursday, but even on the second midterm too. So this is all just kind of for fun and kind of for your information. Because we're kind of in an in-between, part in the class right now. So we're kind of transitioning between, what I consider to be static biomechanics, which is what we've been doing. And then starting next week, we'll be talking about human dynamics. And so we're going to talk a lot more about human motion. So this is kind of an in-between thing. And so, again, it's kind of just for fun. Okay. All right, so biomechanics of balance. And so what do I mean by balance? And so balance is basically just making sure that your body stays upright, okay? And so there's actually a lot of work that your body has to do to maintain your posture and make sure you're standing upright that a lot of people actually are not really aware of. And I think what's fascinating about balance is that it's not something that we actively really think about. And so if you're kind of standing still, even if you're sitting in your seat right now, right? And so your body's actually doing work to make sure that you don't just fall over just spontaneously. And so there's a lot of forces that your muscles have to exert that, that your body just doesn't actively think about. Okay. And so the part of the body that is responsible for this the most is, of course, going to be your core muscles. And so a lot of the muscles in your spine and your neck, and also your lower extremity as well. Okay. All right, so let's go and draw a picture here. Okay. So we're drawing a little kind of a stick figure McGee here. All right, so Mr. Stick Man here is standing up straight, and so he's balanced. He's good. Okay. So let's define some definitions that'll help us with our explanation today. Okay. So the first definition I want to define here is what's called the base of support. Okay. And so the base of support is the area beneath the person that includes every contact point that person makes with the ground. Okay. And so if you're just kind of standing up straight, your base of support consists of basically the outline of your 2 feet. Okay. All right, and so if we kind of draw this out, you know. Okay. So we'll imagine he has like Bigfoot feet. Okay. All right. Actually, I can do that. Let me do that. The right foot's better. The left foot's not good. Anyway, okay. All right. So your 2 feet, you know, if you're just kind of standing up straight, kind of have an outline like that. Your base of support, the way that you can kind of define it is if you draw a box around your 2 feet. Okay. This box right here defines your base of support. Right, so it's the area kind of in between all of your contact points with the ground. And so, of course, you know, you can change your base of support. And so depending on how far apart your feet are spread, if they're closer together or farther apart, that's going to change your base of support. Okay. And so if you have your feet kind of further apart, so let's say that you kind of spread your feet. Of course, that's going to increase your base of support. Okay. And if you bring your feet closer together, then that decreases your base of support. Okay. And so the reason I bring that up is that, you know, when we think about balance, you know, and let's say that, you know, you're standing up and you want to, you want to put yourself in a position where you're less likely to fall over, topple over. Kind of the natural thing that you do is you kind of spread your feet, right? And so if you played any sports, if you've done any kind of, you know, dance or any kind of physical activity, you know that if you spread your feet, you're more likely to, you know, be balanced. Okay? And the reason for that is that, you know, the definition for being balanced is to basically ensure that your center of mass is within your base of support. Okay. Let me draw a free body diagram to kind of illustrate to you why that is. Okay. So here we have our stick figure person again. Okay. And so let's say that, if the person's just kind of standing up straight, not really leaning in any particular way, then their center of mass, will be probably somewhere around here. Okay. And so from the center of mass, we can assume that the weight is going to be acting, acting downwards. Okay. Opposing this weight, of course, making sure that you don't go hurtling towards the center of the earth, is the normal force that the ground is exerting. Okay. And the ground exerts that normal force through your 2 feet. So Fn1, Fn2 are normal forces from the ground that's coming up. Okay, that's going to balance your balance your forces. And so if we kind of draw like almost like a cage, right? And so if we kind of draw if we kind of extend these normal forces upwards, okay, where again, the normal forces there, they define kind of your base of support. Okay. And so as long as your weight or your center of mass is within kind of this cage defined by your base of support, you're going to be balanced. Okay. And the reason for that is, when you start to lose balance, and so, let's say that you start to tip, right? Then your whole body is going to start rotating. And so as long as your center of mass stays within the base of support, these normal forces can act as kind of ways to balance that rotation so that you have no net rotation of your body. And so the key here is to have a normal force on either side of your center of mass. Okay. So to kind of illustrate that point, let me draw an instance where the body starts to actually lose its balance. And so one common way that you can lose balance is that you just keep leaning and leaning over. Okay, and so let me go ahead and draw that. And so, if intuitively we know that if you kind of lean over enough, you get to the point where you start to lose your balance. Okay? And so the reason that occurs is, let me go ahead and draw the normal forces again. Okay? The reason that occurs is that, now, let's say that the person's weight is, outside of this base of support. Okay. And so once again, let's go ahead and extend these upwards. Okay. And so we can see here that we're outside here. Okay. And so if we do a very simple calculation, so let's sum the moments, the net moments of all the forces here around this point. So if we sum the moments around that point, okay. I'm not going to worry about any precise, precise moment arms here. It doesn't really matter all that much. What really matters is kind of the direction for these ones. Okay? And so for this weight here, we can see that it's acting downwards on the left of the pivot point. And so we know this is going to be a counterclockwise moment. So if we kind of write that out, we know that that's going to be a positive moment coming from W. Okay. Fn1 is not going to contribute to the moment because that's exactly where our pivot point is. And so we're not going to worry about Fn1. And then let's look at Fn2. Okay, so specifically the sign. And so if you look at Fn2, it's acting upwards and it's to the right of the pivot point. And so that's also going to be a counterclockwise moment. And so we basically have two counterclockwise moments, acting here. And these forces are in a position where, their directions are fixed, right? And so we know gravity is going down, and so weight is going down. And since Fn2 is a normal force, it's going up. And so W and Fn2 can't change their direction. And so the only logical conclusion here is that because the net moment here is positive, and the body's just going to keep rotating, right? And so you have basically a net moment that's acting on the rigid body of the person's body, and that's just going to keep them rotating. Okay. It's going to keep rotating until he face plants spectacularly into the ground. All right, so that's what happens. So that's what happens when your center of gravity kind of moves outside of your base of support. Okay, and so as long as your center of gravity is inside your base of support, one of these normal forces can act as a counter moment to kind of prevent any kind of rotation. But as soon as that center of gravity goes outside, then your whole body is going to start rotating. Okay. All right. Any questions on this? All right. And so the whole game that you kind of play when you're trying to keep balance is to try to make sure that your center of gravity is inside. Okay. So let's do an example here. Okay. So let's say that we have a person that's standing in a wide stance such that the distance in between their feet is about 0.5 meter. Okay. So this person's standing on the ground. And they're standing in such a posture that the distance between them is 0.5 meter. Okay. We also know that their center of mass is about 0.8 meters off the ground. Or center of gravity, excuse me. And so what we want to determine in this problem is how much can this person lean? How much can they kind of tilt over before they start losing balance? All right, so this problem here is purely geometrical. Okay? And so we don't have to worry about the person's mass or any of that, because we have the location of the center of gravity. We know how wide its stance is. And so we can just do a calculation based on that. Okay? Because what do we know? What do we know about balance? Is that, in order to keep balance, the center of gravity has to be within the base of support. Okay? And so what we want to compute is, what's the outermost limit, that we can tilt and stay within that base of support. Okay, so let's do this. So if a person starts to lean, it's going to look like this. Okay. So this is 0.5 meters. We know that the height off the ground here is 0.8 meters. Okay. And so what we're interested in, if we draw a triangle just like this, let me go ahead and use a different color here. And so if we drew a triangle just like this, okay, what we're interested in is, what's the angle theta of this, of this lean. And so if we kind of, extract this triangle out here, okay, so theta is right here. We know the height of this triangle is going to be 0.8 meters. Okay. The 0.5 meters that we're given here, that's the distance between his 2 feet. And so if we were to draw kind of a triangle starting from the person's midsection going outwards, then this would only be about half of that. And so half of 0.5 is 0.25. And so all we need to solve for here is this angle theta. And so theta here, we can form a trigonometric relationship because this is a right triangle. And so we can make use of tangent. And so tangent is the ratio of the opposite triangle side length over the adjacent one. Okay, so tangent of theta is equal to 0.25 divided by 0.8. Okay. So therefore theta is equal to inverse tangent of 0.25 divided by 0.8. You run that through your calculator, you get 17.35 degrees. Okay. Any questions on that? Yeah.
What was the reason for using points of that?
Yeah, because 0.25, that's the distance between his two feet. And so if you assume the person kind of starting at his midpoint and kind of leaning to the side, then we're only making half that distance. Okay. All right, so that's kind of a pretty simple example. And so in addition to widening your stance, and so widening your base of support, one thing that's often told of people is that another way to make sure that you're more stable and more balanced is to kind of lower your center of gravity, right? So if you crouch down, that's going to increase your stability. And of course, the opposite is true as well. And so making it so that your center of gravity is higher will actually decrease your stability. And so let's do an example to kind of see that. So first, let's say increasing / decreasing the height of the center of gravity. I guess center of mass, center of gravity is the same thing. so let's kind of see why that is. Okay. So I'm going to do kind of an extreme case here, just so you can kind of see. And so let's do a case where someone is holding a very large amount of weight above their head. Okay. And so let's say that this person's holding a very large weight. Just like that. And he's standing on the ground with a somewhat wide stance. Okay, so we're going to repeat the calculations that we did in the previous example, except now our center of gravity is going to be higher up because he's holding this kind of massive weight. Okay. But in terms of the numbers, most of the other stuff is still the same. Okay. And so we're going to assume that the space in between his 2 feet, or the distance between his 2 feet, is going to be 0.5 meter. The height of his body just by itself, the height of the center of gravity, if he wasn't holding the weight, it's still 0.8. We know that the weights that he's holding up, this has a height of 2.4 meters. And we also know the masses of everything involved. And so the person by himself, without holding the weight, the person has a mass of 75 kgs. And the weight that he's holding up, we'll assume it has a mass of 150 kilograms. This person's really, really strong. It's like 350 pounds he's holding above his head, which is pretty crazy. Okay. All right, and so the question we want to ask here is the same thing. So we want to ask, in this position, holding the weight as it is, how much can the person lean before he starts to lose his balance? So the biggest difference in this problem compared to the other one is we need to compute an overall center of mass. Okay? And so we have the center of mass of the person by himself at 0.8 meters, but because this person's holding the weight, there's going to be a new center of mass that we need to compute. All right, and so we're going to compute the height of the new center of mass, okay, so we'll call it HCOM, and we're going to use our center of mass formula. So our center of mass formula, I don't think we've covered it in this class yet. Okay. And so it's a summation formula. And so in the numerator, we have all the products of the masses of the bodies multiplied by their heights. And then on the bottom, we're going to divide it by the sum of all the masses in the system. Okay. All right, so let's look at the numerator first. And so in the numerator, we have the mass of the person's body, which is 75 kgs. Okay. That's his mass without the weight. And without the weight, his center of mass has a height of 0.8 meters. All right, next thing that we need to compute here is the same quantity, but for the weight itself. Okay, so for the weight has a mass of 150 kgs, and the height of that weight is 2.4 meters. And then we're going to divide it by the sum of the masses. And so the sum of the masses are 75 kgs plus 150 kgs. And so we do this calculation. We end up with a height of the center of mass of 1.867 meters. So now that we know the new height of the center of mass, we can go ahead and plug it into the same formula because we're basically in the same configuration here. And so, bless you. And so the theta that we have here is going to be the inverse tangent of 0.25 meters divided by the new height here, which is 1.867 meters. So you run that through your calculator, you get an angle of 7.63 degrees. Right, so that's a lot lower, and so that's consistent with what we intuitively kind of believe. And so if you're holding up this kind of massive thing above your head, you only just have to tilt a little bit before you start, careening towards the ground. Any questions on this? Yeah.
How would stance like having your feet far apart that's with your body? Is that something important? Like how far your feet are from how much weight essentially putting on your body?
Yeah, no, that's a good question. So that's kind of more a question of how your body kind of balances load across your different muscles. So of course in different kind of body positions, it's going to put your muscles in different positions that can kind of balance that load as well. And we'll talk a bit more about that maybe closer to Thanksgiving when we talk about muscle force optimization. But in terms of balance, the wider stance that you have is that it's going to increase this value right here. So if you have a wider stance, you spread your feet wider, you kind of lean more because you kind of widen your base of support. Yeah. Yeah.
2.4 meters. Are you saying that height from like or is it like highest?
It's the height. It's the height of whatever the center of mass of that barbell is. So it's probably where your hands are connected. That seems to make the most sense. Yeah. And so of course the opposite is true too. And so if you were to, let's say that you instead the weight is on the ground and you start to kind of lift it and crouch down, of course that's going to lower your center of mass. Okay? And so in that position, you're going to be a lot more stable. Okay? So kind of the opposite is true as well. So the reason I did this example is to kind of illustrate that, depending on, where your center of mass is in your body in terms of the height, that's going to change the amount of stability that you have. Okay. And so next thing we're talking about is let's talk about, the actual restoring moments that your body can do. Because when your body kind of feels that it's starting to lose balance, your muscles have to kind of react to that to kind of restore that balance. And like I mentioned earlier, earlier today, that this is something that your body kind of does kind of instinctually, because falling down and face planting into the ground is not pleasant, and your body understands this. And so whenever you start to lose balance, even before your center of mass kind of goes outside your base of support, your body's going to react. And so, I can tell you just right now that even if I'm trying to force it, so even if I'm trying to force my body to kind of lean forward, just without me really having to think about it, my leg muscles, my core muscles, they're all acting to kind of try to prevent me from doing that. It's like, are you sure you want to lean that far? And so let's kind of talk about what that is. Okay. And so when the muscles of your body kind of act to kind of restore that, restore your center of mass to kind of the center of your body, we call that, a restoring moment. Muscles providing restoring moment. Okay. And so, of course, if the bigger your muscles are, and the more force that it can generate, the better it is at providing these restoring moments. Okay. And so that's why you see, most of the typical muscles that are associated with you keeping balance, the muscles of your lower extremity, the muscles of your core, of your spine, your abdominal, your hip flexors, things like that. These muscles are a lot larger because, they have to kind of always be doing this work. Okay. And so as an example, let's look at your calf muscles. And so your calf muscles are kind of on the back of your lower leg. So that's actually one of the most important muscles in your body for maintaining balance. Okay. Okay. So let me go ahead and draw a leg here. Okay. So remember, your calf muscles are these muscles kind of on the back of your leg here. Okay. Or what they're primarily responsible for is a plantar flexion movement. Okay. And so when they act, they basically try to point the toes downwards. Okay. Okay. And so when you start to lean forward, okay, what your calf muscles are going to do, they're naturally going to react, and they're going to put a kind of a counter moment to that, and that occurs at your toes. Okay, and so you can test this when you're standing up, start to lean forward. You can kind of feel your calves start to engage, and you can feel kind of the normal force coming up through your toes, because your calves are trying to prevent you from falling over and face planting. Okay. Okay. So the calf muscles are very well suited for this because, first of all, your calf muscle is quite large, right? And so it's one of the larger muscles in your body. And so if it needs to, if you start to lean forward a lot, the calf muscles have they have the girth, they have the power to kind of, right the ship. Okay. Another thing that, another advantage that the calf muscles have is that, if you consider, the fact that, the normal force that the calf muscles are going to be generating around your toes. Okay. But the point at which you actually start to rotate is your heel. Okay. This moment arm that the calf muscles are working with is actually quite large. So, and so of course, the size of people's feet, changes person to person. But generally speaking, the foot is actually, quite long, and that's kind of why we have, decently large feet, is to kind of help us keep balance. Okay? And so the calf muscles kind of have two things going for it. So first of all, it itself is a strong muscle, so it can output a lot of force. And the moment arm provided by the length of the foot is also long as well. Okay. All right, and so these two things together, if you combine together the amount of the raw amount of force that the calf muscle can generate together with, the length of a person's foot, scientists have actually computed, how much moment the calf muscles can generate. Okay. And so on average, for the average person, the moment that it can generate is about 162.5 Newton meters. Okay. So that's pretty big. Okay. And so if you ever start to lean forward, just know that your calves, they have your back. Just kind of think about your daily life, right? So how often do you actually, fall forward and face plant? Almost never, right? And unless alcohol is involved. And the reason for that is your calf muscles are there to help, and they're very well suited for that job. Okay. In contrast, if you consider a task that's a lot more difficult, baby cow, that's right. And so in contrast, let's consider a task that's a lot more difficult, which is doing a handstand. Okay. Okay. So a handstand, of course, is a lot more difficult. And so, I can say with certainty, the vast majority of the population cannot do a handstand. Okay. And there's a lot of reasons why this is a lot more difficult. Because if you're doing a handstand, your arms and your hands are trying to basically play the same role as the feet. Okay? And we already talked about when we did the upper extremity, that your upper extremity has much smaller muscles that they can't output a lot of force. Okay? And so if we kind of look, so let's say this is a person's hand. It's supposed to be hand, it's not a putter. And so if we kind of look at the general anatomy of your arm compared to your legs, right? The muscle that would perform the same action as as your calf muscle would be your wrist flexor. Okay? Okay, and so if you compare your wrist flexor muscles compared to your calf muscles, your wrist flexors are a lot smaller. Okay? And so scientists have measured this as well. And so compared to the feet, the feet, of course, is working with a larger moment arm and it's a larger muscle. And so compared to that, your wrist flexors can only output about 10 Newton meters of restoring moment. So if you compare that to what we have in the feet, which is 162.5, that means it is basically 16 times easier to stand up on your feet than it is on your hands, which kind of lines up with reality, right? And so, it's a lot more difficult. And I think the thing that's even harder about handstanding is that, most of your center of mass is kind of more geared towards your legs. And so when you're doing a handstand, that gets upside down. So your center of mass is also higher than it is before when you're standing on your feet. Yeah.
You just have like massive forearm seconds and calves.
You could, yeah. So the people that can do handstands, you'll see that they have really, really strong forearms because they can, their forearms can output all that restoring movement. Yeah. Large forearms, large hands, if they're just light overall, that helps as well. And so all of those things kind of help with being able to do a handstand.
Hey, Professor.
Is there sorry, the volume here is pretty low. Was someone saying something on Zoom?
Yeah, I had a question. Are you able to hear me?
Yep.
So with the handstand, if your center of gravity varies left to right, kind of like what we just looked at, we can see that like the person loses balance. Is that the same for kind of like in the Z direction? Like, I guess if your hips go like past your head or behind your butt, like, is that kind of like the same as well?
Yeah. So the question is, a lot of the examples that we did previously were kind of talking about kind of left to right balance. But when we're talking about the calf muscle and the handstand here, I'm kind of talking more kind of front to back. And so I think that's kind of an important distinction to make. And so, but the same rules kind of still apply. And so, I think we talked about kind of spreading your feet kind of left to right, but you can very easily kind of both spread your feet and if you are doing a handstand, spreading them front to back as well, and that'll give you more stability in that direction. But typically, I think when someone stands still, and the reason I kind of bring this up, they're not really putting one foot in front of the other, or they're not, if they are doing a handstand, they're not typically putting one foot in front of the other. So a lot of the stability in that direction is provided by either the calf muscles or the wrist flexors. Yeah, but absolutely, if you were to kind of, to have, if you were to modify the location of your center of mass in that front to back direction, either by kind of sticking your butt out or sticking your head out, then that's going to affect your stability in that direction as well. Yeah. I couldn't hear it 100%. The volume is really low, and I'm not sure exactly how to raise it, but that's kind of the was that able to answer your question?
Yeah, that answers my question.
Okay, awesome. All right. Any other questions on this? Okay. All right. So the last thing I want to talk about today is what I think is kind of the most interesting part, which is restoring balance. Okay. Well, in other words, if you do find yourself in a situation where your center of mass is outside your base support and you just start falling over, you start kind of toppling, your body actually can do some stuff to kind of help right the ship. Okay. And what's fascinating about this is that if you've ever owned a cat, or someone that's owned a cat, one thing you've noticed is that the cat you drop it from any height and the cat will land on its feet. Okay? So this is actually something that cats understand really, really well. And it was fun. I was talking to my parents on the phone last night, and they actually watched a documentary on cats, and they kind of explained how cats can always land on their feet. Like, yeah, that's physics. Okay. And so our bodies, the human body, we can do something similar. We're definitely not as adept at doing that as a cat, mostly because we don't have a tail. But there are things that we can do to help restore balance. Okay. And so, before we talk about restoring balance, let's talk a bit about what happens when you start to lose balance. Okay. And so when balance is lost, and so when your center of mass gets outside your base of support, we know that your body is going to start rotating. Okay. And one way that we can describe that is that we can say that the body will start to have an angular acceleration. Right, and so if you start to lose balance, your body will continue to rotate, your angular velocity gets higher and higher and higher until, of course, you hit the ground, okay? And so, the way that we describe it is, you'll have an angular acceleration and your angular velocity will keep increasing and increasing. Okay? Okay. And so the key to restoring balance is to kind of try to prevent this process from happening as much as possible. So to kind of, first of all, if you can, to reverse the angular acceleration. So to make sure to try to make it so that you start rotating in the opposite direction. And then number two is to slow down the angular velocity so you stop heading towards the ground. Okay. And so the key to all of this is the concept of angular momentum. And so, I know we haven't talked about, momentum yet in this class. We haven't talked about especially angular momentum, but that's why I kind of thought this would be kind of a good kind of transition topic. But we're not going to do any calculations with respect to this. We're just going to talk about it in in concept, and then we'll kind of carry over those concepts as we start to talk about human motion. Okay. Okay. All right. And so let's kind of draw a picture here. Okay, so let's say that this person's starting to lose balance. And so if they're losing balance, that means they're rotating in this direction. And so I'm going to use the symbol here, omega body. And so omega body here is going to be the angular velocity of the body towards the ground. And so, again, what we're looking to do is we're first of all looking to slow down W body. Okay, so we're trying to lower its value, or if we can try to reverse it. Okay. Okay. All right, and so to explain this, let's do kind of a quick refresher. Maybe maybe the last time you saw this was all the way back in probably dynamics or maybe physics. And so let's kind of recall the principle of angular impulse and the conservation of angular momentum. Okay. So let's talk about angular momentum first. And so angular momentum, we know, is going to be a product of two things. So it's the product of the angular velocity of the body and it's going to be multiplied by I, where I here is the moment of inertia of the person's body. Okay. And so it's very similar. I think I think it's a little bit easier to remember the conservation of linear momentum. Okay, so when we talk about the linear momentum of a moving object, we know that it's just simply the product of its mass times its velocity. And so this is simply just the angular analog of that. And so instead of mass times velocity, we have moment of inertia times angular velocity. Okay. Okay. And so, and so that's the conservation of angular momentum. And so what that's saying is that in the absence of any kind of external forces, then this angular momentum is conserved. Okay. Okay. We can go a bit deeper into this theory, and if you were to really do calculations of this, you kind of would, because technically speaking, if you're losing balance, you're technically not in a conserved state because you have gravity that's acting on you. So gravity is kind of increasing the amount of angular momentum that you're feeling, because the gravity technically is an external force. But for all intents and purposes, let's kind of assume that angular momentum is roughly conserved. Okay. And so if we make that assumption, that angular velocity is conserved, then we need to ask ourselves, what can we do with our body to kind of slow this down? Okay. Well, the good thing about our bodies is that we're not just solid rocks. We're not just all one big mass. We have multiple segments in our body. Okay. And so since we have multiple segments in our body, what we can do is we can kind of split off or take some of that angular momentum and then put it into other parts of our body that may be spinning. Okay. In other words, we can offload Okay, and so if we kind of move other parts of our body in a certain way, we can kind of offload some of that angular momentum. Okay. And so let's kind of write a simple formula to kind of illustrate this. Okay? And so if we consider the angular momentum of the entire body as a whole, okay. And so that includes, all parts of your body. And so if you start to fall over, your whole body's going to start to have angular momentum. Okay. If we split this up, okay. And so on the one hand, I'll say that we can consider the angular momentum of the trunk. Okay. And so the trunk is, basically your torso. Okay. And we'll consider that to be kind of the majority of your body. And so if your trunk keeps accelerating towards the ground, that's going to give you, that's where you're going to fall down. But let's do this. Okay. And so in addition to your trunk, we also have the arms in our body too, right? And so our arms can actually act as a stabilizer, when we're falling over. Right, and so what this equation tells us is that if we wave our arms in a certain way, we can actually offset some of the angular momentum that the rest of the body is experiencing. Okay. And so it's fascinating because I think a lot of our bodies actually do this naturally. So if you think of like an old school movie, old school cartoon, and you have the villain that's like standing on the edge of the cliff, and the hero kind of pushes them, right? So what is kind of the natural thing to do if you're falling backwards? The natural thing to do is you kind of move your arms in a circle, right? And so you're falling backwards, you're kind of moving your arms in a circle like this, and then that's kind of shown to help, try to help you maintain your balance. And so what's happening in that situation is that, let's kind of draw our falling person again. And so let's say that, this person's falling over, and so they're having a angular velocity in that direction. Okay, so that's going to be the angular velocity of the trunk. If they rotate their arms in that same direction, okay, because of the conservation of angular momentum, you're kind of offloading some of that angular momentum from the body into your arms. Okay. Okay. Right. And so that's one thing that you can do. And so that when you start to lose balance, you can rotate your arms in the same direction to kind of offload that. And so the idea is that, it's really hard to stop your entire body from falling just by rotating your arms. But the hope is that, you kind of slow it down enough so that the rest of your body can kind of catch up. Okay. And so during that time that your arms are rotating, maybe you try to get your foot down on the ground, you try to, get some balance that way, or maybe you're going to move your abdominal upwards to kind of put your body, your center of mass back into, a stable position inside your base of support. Okay. But by rotating your arms, you kind of buy yourself a little bit of time to kind of get your body into a good position. Okay. Yeah.
Can you swing hard enough to absorb all of the momentum?
In theory, yeah. In theory, you could. And so if you had kind of helicopter arms, then you can rotate fast enough to do that. The thing that's kind of stopping you here is, you can rotate your arms a lot faster than your body, but the difficult thing is that momentum is the product of moment of inertia and angular velocity. So your arms, because they're a lot lighter and they're much shorter than your body, they have a lot smaller moment of inertia. And so you're gonna have to rotate them a lot faster than your body in order to get it much higher. Yeah. And you can even test this in a standing position too. And so if you kind of stand up and you kind of rotate your arms, right? So when you rotate your arms, that's angular momentum that's being generated in your body. But to kind of balance that, to make sure that you don't fall over just by doing, arm circles, if you look at your torso is kind of also kind of subtly doing stuff too, rotating in the opposite direction to counteract that. And so, angular momentum is always conserved. It's just that, kind of manipulating it in different ways can get you, different results. Okay. All right, so we're just about out of time, and so I want to give you kind of one more example of this. Okay. And so, if we consider, or if you've ever, maybe you've tried this before, I personally haven't, but I've watched people do this. And so if you were to ever kind of walk on a tightrope, okay. One thing that you naturally do to kind of stay balanced is you put your arms out, right? And so if you're kind of trying to walk in a straight line on a very thin, road or something like that, the natural thing to do is to put your arms out. And the reason for this is that, by putting your arms out, you increase their moment of inertia with respect to your body. And so if you increase their moment of inertia due to the conservation, then you can counteract any kind of tilting that you may do. Okay. And so let's say that you start to lose your balance and you start to rotate this way. What your arms can do is that they can rotate in the same way to counteract that. Okay. And if they're farther apart from your body, then they have a larger moment of inertia to counteract that. Okay? And so by similar logic, another thing that you see people do walking on a tightrope is that they carry a very large stick. Okay. And so they carry a very large stick like that. And that has the exact same logic. And so, carrying a very large stick like that, it's very long. So of course it's going to have a very large moment of inertia, especially if it's a heavy stick. And so doing that will kind of help you keep balance because you can just do very small movements of the stick to kind of correct any kind of body lean that you may be experiencing. Okay. All right. Any final questions on this? Okay. All right. So that's all we got time for today. And so next time I see you guys will be Thursday for the midterm. So please make sure that you come for that. So I have 2 more office hours until the midterm. So I have one tomorrow at 4 o'clock. And then I have another office hours Thursday morning at 9. And so if you have any final questions, please don't be afraid to come and I'll be happy to talk to you. Solutions for homework 3, just so that you can use them for your study, will be up tonight at midnight. And so you can look forward to that. And then, yeah, I guess we'll see you all Thursday. So thank you all for coming today. Hope you enjoy the rest of your day. Best of luck studying, and I'll see you guys on Thursday. Yeah.
I was just saying, maybe forgot about it already, but so how do we for the WB to be just multiplied by the LB, right?
Yeah, no, that's a good question. So I think that's the trickiest part for this problem. And so we kind of draw the trunk just like that. And we know the weight is acting right here. But the lengths that we're given in this problem, we're given this length. So this length is LB. And then this length right here is actually LT divided by 2.
Really?
Yes.
The problem states that? I thought that was the same process. Yeah. Does the problem state that?
It does. Yes, I think the problem states that it acts halfway up, or the backpack is attached halfway up to that. So we know that this angle here is theta. So you can compute this distance pretty easily. And so this distance is LT divided by 2 cosine theta, right? But that by itself is not the moment for this, because the backpack comes up just like that. And so the triangle that you actually have to draw here, you kind of have to notice that this LB is actually perpendicular to the back. And so instead of being an angle with the horizontal here, we now have this angle here, which is that one with respect to the vertical. So this angle is the same as this one because LB and LT are perpendicular to each other. Yep. And so if you kind of take this out right here, and so we say that this is like this, right? And so we know that that angle there is theta. And we want this horizontal distance, right? So this horizontal distance will be LB sine theta. And so that's of course coming back towards the back. And so the total momentum for this is going to be the difference between this and this.
Gotcha.
It's tricky. Yes, it's tricky trigonometry. I almost put on the review poll if you want me to review trigonometry, but I feel like that might be a little condescending. So it's like a static biomechanical analysis. But yeah, that's definitely, I think, the trickiest
Yeah,
thing.
I was looking at that earlier on. Asking again, but yeah.
Trig is hard. I remember writing this problem and I had to redo my solutions like twice because I was like, oh yeah, I don't remember trigonometry. Yeah. Okay.
Similar question. So I was pretty confused in the FM. So we're using FMB in both cases.
So it depends. And so for determining, which one's going to act, I would do the sum of the moments without the muscle forces. So we have two cases, right? We have one where the angle is 85 degrees. I think the other one's like 55. And so, if you do it for 85 first, compute the net moment that's resulting from the weights, and then see what sign it is. And so it's not going to be 0. And so if it's a positive, that means if your net moment is positive, that means it's going to want to rotate that way. That means you're going to need a negative moment from the muscle to kind of counteract that. And so I position these muscles, very deliberately, because one of them is going to give you a clockwise moment, and so the abdominal muscles are going to give you clockwise, and the back muscles are going to be counterclockwise. And so depending on the sign of the net moment, then you're going to need one or the other. And I picked the two angles 85 and 55, so that one case is one direction, the other case is the other direction. Yep. Yep.
So for the X, I'm not sure what I'm doing.
I don't know why.
But like,
Yeah. So I think a lot of people are making this because I think I drew that figure. I need to redraw that figure. And so the main thing here is your muscle force. And so I think I did one example in class which was like this, but I think it confused everyone because in the class
it has the.
yes, exactly. But in this one, I gave you kind of a direct line from where the muscle attaches to the joint here. So it's actually not simple. So if you kind of draw this out, so this here is the joint. And this is the muscle force. The angle that I gave you is this one right here, theta M. And so if you kind of draw a triangle, because remember the moment arm is always the minimum distance between the force vector and the joint.
Why do we care about the X? You're right.
And so this is the distance that we want.
Yeah.
This line right here is perpendicular. And so this length right here, if we know that this length is LM, is LM sine theta. And so the moment for that muscle is just that. And so you don't need to add any of the angles for the muscle. And then you would just have one term. And so we have FM, LM sine theta M. And then for your weights. Yes. So for the weights, you have to keep in mind that you kind of extend, the joint is up here. And so when you're computing the moment for the weight of the leg, you need this horizontal distance. And so it can be L1 LL cosine theta, and then you need to subtract this distance right here, which is LM cosine theta. So if you kind of draw this figure, so this is the weight of the leg. This is L1. This is LM. This angle here is theta H. This angle here is theta. And so, the distance that we want is actually this distance right here. Right? And so to get that distance, you would do L1 cosine theta minus LM cosine theta H. And so because this L1 cosine theta, that'll give you the distance between here and here. But then what you actually want is this distance. And so you need to subtract this distance right there. And so that of course applies to Fn as well. But Fn you do L1 plus L2 cosine theta.
And then I need help starting the movement.
Yeah. So for C, that's so thing with C. So what I've been telling people is that we have a question of which muscle force is going to be active, right? And so let's ignore just the muscles for now. And so what I've been recommending people for C is that you just sum up the moments just from all the weights, and then you check and see which sign it's going to be. And so if it's positive, then you know you need a negative moment from the muscles to counteract that. And if it's positive, you know that you know, same thing. And so, but the same thing applies here. So for these weights, you know, because they're vertical forces, the moment arm for them is going to be purely horizontal. And so, you know, let's do WH, just so you can see. So WH. So here's the joint. You know, this angle here is what I call theta. And so this horizontal distance will be, so this is LT, right? And so the horizontal distance here will be LT cosine theta. Okay. And so the moment for WH would be WH times LT cosine theta, and that would be negative because it's a clockwise one. And so very similar for the WT, it just be LT divided by 2. The one that's tricky here is WB. And so that's what I was kind of showing people up here. Okay. And so for WB, you know, not only do we have this distance here, LT divided by 2, that's where the backpack kind of extends outwards, but then we also have to account for this LB right here. But what we do know is that LB and LT are perpendicular. Okay. And so we can use that information, the fact that, you know, these are perpendicular, and we know this angle here. Since this angle is the angle that the trunk makes with the horizontal, that means you can draw the same angle here with respect to a vertical line. So if you draw this kind of triangle here, then that horizontal distance would be L sine of theta. And so same idea that you did for this one here. So that you would then just take the difference between these two to get the moment on for yeah, thank you. Yeah.
I had a question about finding WB for 85 degrees. So prior to, I guess, last homework or this homework, I had a habit of, when it comes to vectors like this, what I would do was, let's say I'm taking a moment of something here, and there's a vector here. And basically what I'm trying to say is, you know how I noticed that you would take the parallel to the line, so you don't have to take the cosine of this. I would try and make this horizontal and then make this vertical, assuming this one was a vertical. But since I realized this new kind of method of doing statics, I've been trying to implement it. So coming and doing this one, what I tried to do was, this is the, you know, point, and this is parallel. So I tried making this come out like that, and then just doing the moment, it would be LB times WB, an angle, whatever it is. But it didn't come out, and we ended up doing something wildly different that took me a long time to understand. It did come up with the correct answer, but I was just gonna run it by you.
Yeah. No, this is actually a clever way to do it. You know, in this case, this component here, the moment arm for that is exactly.
You're supposed to play by that, right?
The difference here is that, you know, the kind of the origination point here is up here. So you would actually have a moment from the other component as well. Whereas normally for the muscle force here, you know, this distance that we're given. And so if you kind of break this up into components, then, you know, you would have the perpendicular component. So then the moment arm for that would be exactly this. But the parallel component, it wouldn't contribute to it. But for this case right here, we have another component here in addition to that one, and this one will contribute.
So you had to treat both.
Exactly, and so then for the moment arm for this one would be LT. So I think if you do that, then you get the same answer. Yeah, the only thing is, that's why I think it's a clever approach. I didn't think about that before. It's just that, you know, making sure that you break up the WB into these components, you have to make sure.
Yeah, that's what we had done, because I was working with Gasser and we figured it out that way, so.
Oh, that's clever. I like that a lot. And that's yeah, you just kind of have to make sure you.
Coming to the next part, bad posture. I'm having a little bit of trouble as well. Maybe quite my thoughts. I know you're saying class.
Yeah, I have another class right now, so maybe
Okay, yeah.
maybe we want to talk after that one, or if you want to send me a signal, then I'll.
Okay, yeah. Okay, too late.
Yeah, but I have another class.
You're right.
It's just reaction. I'm not getting the right.
or it's like, let's say that the X,
Yeah.
there's only two forces. And I'm suspecting I'm using the wrong angle. I'm using the angle that's given by the F.
Okay. Are the reaction forces at the X and Y or they along? Because the ones I gave in the answer are just X and Y.
I'm treating them as X and Y.
Are rated X and Y.
I just drew them like that.
Yeah, take a picture of it. Let me check. I'll check the notes and go back.